Hello student, welcome in Department of Nanoscience and Nanotechnology S.Y.B.Sc paper second class. In last two lectures, we have been seen the second property of mechanical properties, that is tribology. In that, we have been seen the three components of tribology science, that is friction, wear and lubrication. In today's lecture, we will see the third property of mechanical properties, which is elasticity. Elasticity. When we apply an external force upon a body, then there is a change either in size or shape or both of the body. This force is called deforming force. On removing it, if the body again acquires its original size or shape, when the deforming forces are removed, then such a body is called perfectly elastic body. If the body does not come back to its original size and shape when the deforming forces are removed, then such a body is called perfectly plastic body. For example, when one end of rubber cord is held in one hand and the other is pulled slightly by the other hand, the length of the cord is increased. However, on releasing the rubber cord, it again comes back to its original size and shape. This property of the substance is called elasticity. The body in which this property is found is called elastic body. Hence, elasticity is that property of the material of the body by virtue of which it opposes any change in its shape or size when deforming forces are applied to it, and recovers its original state as soon as the deforming forces are removed. Actually, no body is perfectly elastic or perfectly plastic, but all bodies behave in between these two limits. However, cords can be considered as almost perfectly elastic, and wax or wet clay can be considered as almost perfectly plastic. Rubber, steel, copper, silver, etc. are examples of elastic bodies, while wax, plasticine, modeling clay, etc. are the examples of plastic bodies. Then, limits of elasticity. Elastic bodies recover their original state when the deforming forces are removed. However, there is a limit to this deforming force. The body will not come back to its original state. It will be permanently deformed. Hence, the maximum deforming force up to which a body retains its property of elasticity is called the limit of elasticity. If further force is applied, then even after the removal of deforming force, body will not come back to its original state. For example, if a small load is applied at the lower end of a wire suspended vertically from a rigid support, the length of the wire increases. When the load is removed, the wire acquires its original length. If we increase the load step by step, then a stage is reached when, on removing the load, the wire does not recover its original length, but its length is permanently increased. Thus, its property of elasticity is destroyed since the deforming force is applied beyond the limit of elasticity. Next is stress and strain in solids. First one is stress. When an external force is applied to a body, then at each cross section of the body, an internal restoring force is developed which tends to restore the body to its original state. This restoring force possesses following properties. First property, the force of restoration acts in opposite direction to the force of deformation. Second is, as the deforming force increases, the force of restoration also increases. Third one is, at the time when maximum deformation has occurred, then the force of deformation is equal to the force of restoration. At this time, the deforming force or the restoring force is maximum. Stress is defined as the internal restoring force acting per unit area of cross section of the body. Since in equilibrium, the restoring force is equal in magnitude to the external force, the stress is measured as the external force per unit area of cross section. Hence, stress is equal to restoring force divided by area over which it acts, or stress is equal to applied force divided by area. Dimension of stress is 1 in mass minus 1 in length and minus 2 in time. The SI unit of stress is Newton per meter square and the CGS unit is Dyne per centimeter square. Depending upon how the external forces are applied on a body, there are three types of stresses. First, longitudinal stress. If F is tensile force acting on area of cross section A, then the longitudinal stress is the ratio of tensile force acting per unit area of cross section. For example, let us consider a wire of length L and radius R. Its one end is clamped to a rigid support and a weight mg is applied at the other end. Suppose within the elastic limit, its length is increased by L, then longitudinal stress is equal to force upon area of cross section, that is F by A. F is mg and area of cross section is pi r square, which means mg divided by pi r square. Next is normal or volume stress. When a uniform pressure is applied all over the surface of a body, the volume of the body changes but its shape remains unchanged. The normal force acting per unit area of the surface is called the normal stress or volume stress. Normal stress is equal to normal force divided by area. Normal force is F and area is A, means F by A, that is equal to delta P, where delta P is change of pressure on the surface. Third one is tangential or shearing stress. When a body is acted upon by an external force, tangential or surface of body, the opposite surface being kept fixed, it suffers a change in shape, its volume remaining unchanged. Then the body is said to be sheared through an angle theta as shown in figure. The body acquires shape like a pack of cards on which tangential force is applied at the top. The bottom remains at the same position whereas the upper layers are displaced through an angle theta as shown in figure. The ratio of shearing force or tangential force applied per unit area of cross section is called shearing stress. Therefore, shearing stress is equal to tangential force divided by area of cross section, which is equal to F by A. Hence, we see that in shearing, only the change of shape takes place while volume of the body remains same. Next is strain. Strain is defined as the change in dimensions per unit original dimensions of a body when an external force is applied to it. Depending upon the way the deforming forces are applied to a body, there are three types of strains. First, longitudinal or tensile strain. When a body is subjected to longitudinal stress, then it elongates. The change in length, that is small l, per unit original length, that is capital L, is called as tensile strain or longitudinal strain. Therefore, tensile strain is equal to change in length divided by original length, which is equal to small l divided by capital L. Second one is volume or normal strain. When a body is subjected to normal stress, then its volume changes. The ratio of change in volume to original volume, capital V, is called volume or normal strain. Therefore, volume strain is equal to change in volume divided by original volume, which is equal to delta V divided by capital V. Third one is tangential or shearing strength. When a body is sheared, as shown in above figure, through an angle theta, then theta is called shearing strength. Shearing strength is equal to tan theta, which is equal to lateral displacement of any layer divided by its distance from the fixed layer. As shown in figure, the lateral displacement is AA1 divided by its distance from fixed layer, which is AD, or BB1 divided by BC, or x divided by capital L. Since theta is very small, therefore tan theta is equal to theta. Hence, theta is equal to x divided by L. Since strain is a ratio of similar quantities, it is a dimensionless and unitless quantity. Next is Hooke's law. In the year 1679, the scientist Robert Hooke gave Hooke's law on the basis of scientific observation and analysis of his experiments. According to the Hooke's law, within the limits of elasticity, stress is directly proportional to strain. That is, within the limits of elasticity, stress is directly proportional to strain, or stress divided by strain is equal to constant. That constant is called as modulus of elasticity. Hence, modulus of elasticity is defined as the ratio of stress to strain within the limits of elasticity. Dimensions of modulus of elasticity are same as that of stress, that is 1 in mass minus 1 in length and minus 2 in time. Its SI unit is Newton per meter square, while CGS unit is Dime per centimeter square. Depending on the types of stress and strain, there are three types of moduli of elasticity. Young's modulus. Young's modulus is defined as the ratio of longitudinal stress to longitudinal strain within the limits of elasticity. It is denoted by letter Y. The Young's modulus is applicable only to solids. Young's modulus Y is equal to longitudinal stress divided by longitudinal strain. Longitudinal stress is mgl divided by longitudinal strain. We can also write capital Y is equal to F into capital L divided by A into small l. Since Y, A and capital L are constants, we can write YA divided by L is equal to constant, which is called K, or F is equal to K into L. Hence, the change in length is directly proportional to the applied force. Above equation represents Hooke's law in its original form, where K is the force constant. Second modulus is bulk modulus. Bulk modulus of a body is defined as the ratio of volume stress to volume strain within the limits of elasticity. It is denoted by capital K. The bulk modulus is applicable to all solids, liquids and gases. Bulk modulus K is equal to volume stress divided by volume strain is equal to delta P into V divided by delta V. Bulk modulus is also called incompressibility and its reciprocal is called compressibility. Bulk modulus is also called incompressibility and its reciprocal is called compressibility. This is why more is the value of bulk modulus, more incompressible the body is. Hence, compressibility is equal to reciprocal of K, means 1 by K. In general, solids are less compressible than liquids or gases because of their rigid atomic structure. Liquids are more compressible since the atoms are less tightly bound to their neighbor. Third modulus is modulus of rigidity, that is eta. Modulus of rigidity is defined as the ratio of shearing stress to shearing strain within the limits of elasticity. It is denoted by eta. The modulus of rigidity is applicable to solids or gases, modulus of rigidity eta is equal to shearing stress divided by shearing strength, which is equal to F by A divided by theta, or F by A divided by X by capital L, which is equal to capital F into capital L divided by AX. Steel is more elastic than rubber. Elasticity is the property of the material of a body by virtue of which the body opposes any change in its size or shape caused by an external force. Clearly, greater is the force required to produce a given change in size or shape of a body, the more elastic the body is said to be. If we take steel and rubber wires of equal length and same area of cross section, a large force will have to applied to the steel wire in order to produce equal extensions in their lengths. Suppose two wires of same length L and same radius R, one of steel and the other of rubber, are suspended from a rigid support. Suppose and applying equal weight mg to their lower ends, their lengths increase by Ls and Lr. If Ys and Yr are the Young's moduli of steel and rubber respectively, then Ys is equal to mgl divided by pi r square into small ls, and Yr is equal to mgl divided by pi r square into small lr. Therefore, if we take the ratio of Ys and Yr, the common part is cancelled, then Ys divided by Yr is equal to Lr divided by Ls. Experimentally, Lr is greater than Ls, hence Ys is greater than Yr. Thus, steel is more elastic than rubber because the value of Young's modulus is more for steel and less for rubber. Next is stress-strain curves. According to the Hooke's law, within the limits of elasticity, stress is directly proportional to strain, but this proportionality exists for small strains only. Let us consider a wire of uniform area of cross-section which is clamped at its upper end by a rigid support, and a load is applied at its lower end which is gradually increased. As a result, the length of the wire goes on increasing. A graph between a longitudinal stress and corresponding strain is a curve as shown in figure below. As shown in figure, the initial part OA of the graph is straight line, which indicates that up to the point A, the increase in length is directly proportional to the load. Next point is explanation of elasticity on the basis of atomic model. Matter is made up of ultramicroscopic particles called atoms. The atoms of solid are held together in a regular array by electric forces in a way as if they were connected by spring. As shown in figure, all atoms are connected by spring. Under these forces, the solid remains in its natural equilibrium state. Inside the solid, the distribution of positive and negative atomic charges is such that when the solid is in its natural equilibrium state, there is no force acting between the atoms. If, however, the solid is compressed by an external force, the distance between the atoms decreases. Now, the distribution of charges in atoms rearranges in such a way that there is net force of repulsion acting between the atoms. This force is called interatomic force. When the external force is removed, the interatomic force pushes the atom back to its original position so that the solid also returns back to its original condition. Similarly, when a solid is stretched, then the distribution of charges in the atoms is rearranged in such a way that there is net force of attraction between the atoms. When the external deforming forces are removed, the atoms come back to their original condition. Because of this force of attraction, thus causing the solid to come back to its initial position. If this case, there is permanent dislocation in the positions of the atoms, and on removing the external force, the solid does not go back to its initial position. In case of a wire, if we go on increasing the load on it, then ultimately the wire will break.